Okay, it's 12 o'clock. Hello, everyone. Thank you for joining the webinar. And today's webinar is sponsored by the Stripe Center. And Stripe is the U.S. DOT Region 4 University Transportation Center. And so there's including 10 universities and college for this one here. And today's presentation is a collaborative research project between Georgia Tech and Auburn University on the G4, quantitatively evaluate work zone driver behavior in support of congestion mitigation modeling, calibration, and validation. This is the one that Stripe sponsor university. And next slide, please. So during the presentation, if you have a question, please put it in the chat, and towards the end, we are going to respond to your question. In addition, there's a survey that you can fill that up and the end of the presentation. Next slide, please. So at the very beginning, I would like to acknowledge the sponsor by the UTC Stripe for this project. In addition, my research team at Georgia Tech, the graduate student and undergraduate student working on this, as well as the input and support provided by the Georgia Transportation, as well as my partner from the Auburn University, and including their PhD students. Next slide, please. The following here is the presentation we're going to make today. We have several presenters presenting, including myself, two of my PhD students. Later on, they'll briefly mention their name, and then also the partner from the university, Auburn University, Nick, as well as Dr. Turochy. And then, so this is a topic research problem. We're going to start with that, and then talking about research objective. And then there's two major components that we are going to talk about from Georgia Tech: AI-based data extraction system and the driver behavior study. And then I'll turn into the Auburn University to talk about application of traffic simulation. Next slide. So as you know, that work zone, the heavily related to safety. So especially right now, the increasing number of the maintenance rehabilitation projects. So here's showing the number there, 43% of the public work here in terms of maintenance rehabilitation. And this one here is expected to increasing with the incoming infrastructure investment bill. And as you can see, that is based on the 2019 figures, that probably going to increase too when the number of the maintenance rehabilitation projects increasing. So estimated almost 115,000 crashes, as well as more than 800 fatalities. So that's heavily related to safety. Next. So the topic we're talking about a work zone is also impact mobility besides the safety. So there's 10% of a work zone contribution to the overall congestion, as well as 24% related to the unexpected freeway delay. So it's impact both the safety and mobility. Next slide, please. So kind of background, the study we have is understanding the real world driver behavior and traffic characteristic is important for designing and optimize work zone traffic control configuration and for work zone safety and mobility. And the work zone driver behavior like merge point, those are required or essential for the traffic simulation. However, this information is often not available. In current driver behavior study in work zone, a lot of time is based on historical data, not actual the work zone driver behavior. So what we're thinking about is a widely available traffic camera image available. And so provide an opportunity for us to study the driver behavior and traffic information using the artificial intelligence and data mining. And previously at Georgia Tech, we had the NCHRP project and continue for this UTC project. Previously, we have using the camera image, but I think through the manual process. And this time here, we try to explore, can we using the AI with machine learning to automatically extract the data. Next slide, please. So therefore, this is earlier I mentioned it to you, the opportunity here, the traffic camera image, either the one in the work zone camera image, or typically in Georgia, Atlanta, there's a navigation image. Those are widely available. So the whole idea here in this study is, can we take advantage of those images available to study the work zone driver behavior, which is typically or often not available. So that way there we can support the simulation model, etc. So, so this is the one of the background information. Next one here. So this is objective. We have three objectives here. The first one here is to assess the feasibility of developing an AI-based work zone driver behavior and traffic information extraction system using widely available traffic camera image and AI. The second is perform statistical analysis of the work zone driver behavior and traffic information using the AI extracted data with the QA/QC tool. And the purpose for this one here, we want to demonstrate is the data we directly using the widely available camera. Can we study the driver behavior? Can we kind of get some of the behavior data information out of that, as well as to support subsequent the traffic simulation modeling. And the third one there is apply the field collected lane change driver behavior to enhance the simulation modeling practice and provide recommendation for agency. This is the one you can first time seeing that, yes, this is real world data, driver behavior, and with a statistical distribution now fit into modeling. So how they can provide a new information for the modeling. And next one. So this is the one I'll turn into Lucas to talk about the AI system. Yeah, Lucas.
Yeah, thank you, Dr. Tsai. Hi, everyone. My name is Lucas Yu. I'm a second-year PhD student working with Dr. Tsai. So in this portion, I'm going to talk about a little bit about the AI-based data extraction system that we developed for this project. Next slide, please. So just a overview on the data extraction system. So the system, how it works is pretty straightforward. Mainly, you have three parts of the system. You have the data extraction part, you have the data processing, data acquisition part, you have the data extraction and data processing part, and also you have the results aggregation portion. So since we want to take advantage of the widely available traffic camera, so for data acquisition, it typically is pretty straightforward as copying or streaming and recording the traffic video from traffic cameras and feed that data into the traffic into the data extraction system. So in the data extraction portion, we're actually using two parts that feed into the actual data extraction. The first portion is to take the video and then perform image extraction and the vehicle detection. And on the other hand, we ask the user to provide some kind of the label on the scene, on the video, and provide that kind of information alongside with the vehicle detection results to the data extraction system. And from the data extraction system, that's where we want to get the useful information, such as traffic count, traffic speed, as well as traffic emergent behavior, and aggregate them into a meaningful format that can be used later. So next slide, please. So for the traffic detection and classification portion, we are using a deep learning object detection model for doing the vehicle detection and classification. So the deep learning model we're using is ULO version number 3. This model is known for its fast processing time. It can achieve real-time detection while also being pretty accurate. The model is being trained. We take a pre-trained model. We didn't do any specialized training on the model. Even with the pre-trained model that was trained on Microsoft's COCO dataset, that's common object in context dataset, we can see for doing such a vehicle detection task, it's able to do a fairly good job while also being able to classify heavy vehicles like semi-trucks from smaller vehicles like the passenger cars. Next slide, please. So on the other hand of the vehicle detection, we have asked the user to input labels. So when we say labels, we can just annotate the scene to inform the data extraction component something about the video. So the labels we ask the user to input, there are three types of labels. One is merge zone labels. So since we want to extract the merging behavior, and we don't necessarily want the merge results to be exactly how much meters or how many feet before the walk zone, we divide the merge zones, merge locations in terms of the zones, and then we ask the user to provide the known locations based on the image. And for the vehicle and for the vehicle lane change, we need to know where the lane is for the extraction component. So we also ask the user to label the traffic markings, lane markings. And for traffic speed and the traffic volume, we are using what we call a virtual speed loop to extract the data. So we ask the user to just draw two reference lines based on the pavement markings, so we know they each has a set distance between each other. So we can use this kind of checkpoints to extract traffic volume, traffic speed based on the detection results. Next slide, please. So with all those information feeding to the data extraction components, and we're able to use both information to extract traffic count, traffic speed, and traffic merge locations. So the main task for the data extraction component is actually to establish tracking. So what I mean by that is, although we're using a fairly powerful deep learning-based vehicle detection, it is done based on image by image. So it does not know whether the detected vehicle in this frame is the same vehicle as in the next frame. So to overcome this, the data extraction component is tracking the bounding box for the detection results across different number of frames for us to establish tracking and be able to produce traffic count, speed, and merge location information. For example, for traffic count, we're utilizing a shortened tracking between two very small number of frames, like 2 frames, and to identify for a vehicle when is this bounding box or this vehicle first cross one of the checkpoints. And that's the timestamp we're going to count that vehicle. Similarly, for traffic speed, because we're using a virtual speed loop, so we're checking the interaction between the bounding box and the reference lines, 2 reference lines, when enters, when it exits. So we're utilizing a longer term tracking over a longer period of time, and with all the vehicle, you can call it a trajectory or a vehicle movement. With all the vehicle trajectory, we can also obtain, based on using the lane marking labels, we can identify in which zone a vehicle has to make a merge move or a lane change move. And all those informations gets aggregated into a meaningful way that we can be used, for example, in a driver behavior study. However, I do want to point out that because we are developing a preliminary version of the AI system, we also have a tool with graphical user interface to do the QA/QC process. So we can see as all the data extraction happen, and also the user can intervene if he sees any errors. So we can demonstrate if all those data extraction is done properly, how it can impact or how it can be very meaningful for a study, for a driver behavior type of study. So, and that's where I'm going to transition to Cibi, who's going to talk about the driver behavior study that we've done using the extracted data.
Thank you, Lucas. My name is Cibi Pranav, and I'm a 5th-year PhD student working along with Dr. Tsai at Georgia Tech, and I'll be continuing on the application of the data extracted from the AI system and how we can use that for studying the driver behavior. In this example, what we are talking about is driver merge locations and the merge behavior using traffic speed, lane change data, and analyzing the lane change distributions. We're going to see how different factors are impacting the driver behavior. So for the data collection part, we worked along with Georgia DOT, who helped us set up work zones at Interstate 95 near Savannah, Georgia, where we collected the data. And for collecting the data, we used mobile post, which we could pull it into the work zone paper, and facing the upstream, we record the scene. And we established 10-meter high so that it can capture a good amount of upstream length. And using this data, we performed our analysis. Going on to the field test design, since the purpose of our study was to objectively compare different factors like the roadway geometry, traffic density, vehicle type, and the type of lane closed inside or outside, and how it impacts the driver merge locations and its distribution. So to account for different factors, what we did is we created scenario-based field data collection design, in which we identified 5 scenarios from the 2 work zones and collected 30-minute videos in each of them. And the cases that we have used that are scenarios are like, we have a straight roadway with the outside lane closed and having a low traffic density, accounting for the geometry, the type of lane closed, and the traffic density. Then we had a straight roadway, outside lane closed, and medium density with high density. So these were at one site. And then we had another case in another site where we had a curved upstream section before the work zone. And the final case was a work zone in which the inner lane was closed. So we identified 5 of these cases, and it is noted that the pre-work zone speed limit was about 70 miles per hour. So how did we perform this analysis? So what we did is we broke down the zones into to group the different driver merge locations or lane change locations in the work zone and analyze their distribution. We defined 4 zones. So as you can see in this figure, there are the zone 1, which covers the transition area, and then the advanced warning area was divided into 3 more zones. Zone 2 from 500 feet off the beginning of the transition area upstream till the first 500 feet. The second 500 feet is zone 3, and further up is zone 4. To perform the analysis, so we classified driver merge decisions. So we call as early merge, which is when the drivers are merging in zone 3 and 4. Then we have the late merge, which is when drivers are merging in zone 1 and 2, which is the transition and the first zone. And then we call a dangerously late merge, which is when drivers are merging inside the transition zone. And this is particularly dangerous because the drivers are exposed to constantly changing taper. And also it could lead to congestion if people are stopped on there and trying to move into the through or the open lane. So to study how different factors impact the driver merge locations, we devised experimental test cases in which we identified individual factors. In the first case, we analyzed the impact of vehicle type, how the cars and trucks perform in the merge distribution. And the classifications are coming from the AI system. So that was an application of using the system. And then in the second case, we are talking about the impact of roadway geometry, whether how the straight versus curved roadway sections are impacting the driver merge locations. Then we have the impact of traffic density and also the impact of the lane closed. However, for the interest of time and to present the preliminary findings and to show how this driver behavior analysis can be performed, we are only taking the 2 cases, and I'll be talking about them. So here are the results from our study. So in the first case, when we are comparing cars versus trucks, you can see two rows of figures, cars and trucks, and each of the bars represent the zones. So zone 1 is represented by red color, zone 2 represented by yellow, zone 3 by blue, and zone 4 by green. What we can see is that in case of trucks, there are a lot more green and blue boxes which are going over 50%. And this indicates that truck drivers are predominantly merging earlier in zone 3 and 4 than the car drivers. And this behavior could be potentially attributed to, say, the longer sight distance available to the truck drivers by virtue of their higher seating, or the truck drivers are professionally trained so that they are more defensive and they merge earlier. Or they could also be that semi-truck require longer distance to complete the lane change at high speeds, and hence they choose to merge early. But this study is giving us more insight to study some of these behaviors in detail. But this is a start for that. And this gives us actual real world behavior. And the second case that we take on here is how the car drivers merge in terms of upstream straight and a curved section. And what we can find is that the car drivers merge later in the curved upstream section in scenario T than they do in the straight upstream section, scenario A. And there is a 14% increase in the car merges in zone 1 and 2 when the curved upstream section is present compared to the straight upstream section. Why is this happening? It is likely because drivers have a limited sight distance, especially the car drivers, in curved upstream section, and they notice the work zone taper later than in a straight section. And therefore, they tend to make late mergers when work zone follows a curved geometry. Coming on to the summary of the AI system and the driver behavior, what we find is that the preliminary version of AI-based work zone traffic and driver behavior extraction system was developed, and it takes advantage of the widely available traffic cameras and the machine learning, all the state of the art. We demonstrated that the feasibility of using such method for extracting vehicle speed, vehicle volume, and lane change locations. So very promising. Indeed, it's also promising the extracted information for studying the driver behavior, like the cases I just presented. And based on the observed work zone driver decision behaviors and the distribution, transportation agencies can make adjustments in their work zone traffic controls, for example, changing the length of the taper in case of curved roadways upstream section, so that drivers can visualize the taper and can merge earlier, or present different sign locations based on the actual driver behavior in those locations. And not only that, it is also helpful to perform these statistical outcomes can help in simulation modeling. And I would like to turn on to Dr. Turochy and Nick for their presentation about the applications of traffic simulation. Thank you.
All right, thank you, Cibi. I'm gonna go ahead and switch to sharing my screen. Hopefully we don't have to struggle through this for too long. And you should see a picture of a river, and then I'm going to put our presentation up on the screen and turn things over to Dr. Turochy to kick us off here.
Okay, thank you, Cibi, and thank you, Nick, and thank you everyone for attending and taking time out of your day to learn about some of the cool stuff that we're doing here in terms of making good use out of the traffic data that's been collected by the Georgia Tech team in that work zone on I-95. So for the next few minutes, we'll talk about the Auburn portion of the work. I'll just set the stage for a moment or two and then turn it over to Nick. So to get started on that, we're looking at exploring practical uses of freeway work zone lane change behavior data from the system that the Georgia Tech team has developed. So next slide. The data provided by this process, just to kind of talk about a couple or reiterate a couple of the points that the Georgia Tech team made, is we're looking at the lane change distance in terms of how far in advance of the lane closure or how far upstream of the taper does traffic merge. These are data that are not easily or typically collected as part of a regular work zone process. So we have quite a resource here that we're trying to make some use out of. And the way that we can make the use out of it is to use the PTV Vissim software, one of the more commonly used traffic simulation software programs, to maximize the usefulness of this fairly unique data that's been collected here. With recent enhancements to Vissim in 2016, for example, the time headway distribution or gap distribution between vehicles in the traffic stream was modified from being a static or deterministic value to a distribution. And that more realistically reflects, of course, what happens in traffic, because not every driver follows sort of the same practices in terms of distancing themselves from the vehicles ahead of them. And more recently, specifically last year, an update to Vissim allowed the lane change distance, in other words, in advance of the taper, to be entered as a distribution rather than a single static deterministic value. So this study that we're working on here is likely one of the first to really make full use of these capabilities to more realistically simulate traffic and capture these items of variability. So next slide. Let's I'll set the stage here for Nick and then turn it over to him. In terms of the Auburn task, the first phase was to vary those key input parameters like lane change distance distribution, headway distribution, and so forth, to see how well the model can replicate the field data that we have from that site, and specifically speeds, which is a pretty typically used measure to calibrate a traffic simulation model. And then the second phase that Nick will describe, sort of the two parts of work that the Auburn team did, was to take the best values that came out of phase one in terms of accurately replicating what was observed in the field, and then take a look at how under various traffic volume and roadway geometric characteristics, as well as different work zone configurations, that a model can be calibrated. And that ultimately leads to recommendations for traffic modelers and road owning agencies in terms of trying to estimate the impacts of their work zone scheduling decisions. So at this point, I'll turn it over to Nick Jehn to give us the highlights on the work that the Auburn team did. And Nick recently completed his master's degree here at Auburn. Nick, I'll turn it over to you to finish your introduction and get into the deeper part of the work that we did.
Great. Thanks for the introduction, Rod. So as Dr. Turochy mentioned, I graduated from Auburn a few years ago with a master's degree. You can see my beard on the screen. I'm younger than I look. But I'm now a consultant. So I work for Kinley Horn & Associates in Charleston, South Carolina. And before that, I actually worked for the Department of Transportation in Kentucky as well. So what I like to say is that I've worn many hats, and I try to continue to wear those hats as I work each day. And you'll hear me reference back to the fact that, in consulting, we do X a couple times throughout the presentation. I think it's helpful to be able to draw those correlations and figure out, what is ultimately going to be the practical application of what we're doing here from a research standpoint. So to kind of back up at a high level again, and just to look at what the problem is and what our objective was here. So number one, as you can see by my beautiful artwork on the right side of the screen, with the arrows that are zigzagging in all different directions, when we develop a traffic simulation model, we always start with a base model where we develop our baseline geometry and we get our traffic volume inputs, and we have some type of starting point for the driving behavior coded in that model. But from there are really, hundreds of different paths that you could take to ultimately get to that green pin on the right side and get to a calibrated model. And because of that, while there exists a substantial amount of research towards guiding modelers and selecting those driving behavior parameters for calibrating their models, particularly for modeling freeway work zones, there's still quite a large gap in the body of literature, and there exists a need to limit the ambiguity and the inconsistency that results from not having clear-cut guidance as to which one of these 10 paths that we've got shown on the screen you should take to go from your base model to your calibrated model. And why that's important is, there are a number of, I like to refer to them as knobs that we turn as we're trying to calibrate our simulation models. And depending on which way we turn those knobs, the ultimate application of our calibrated model to theoretical scenarios that we're trying to understand is going to change, and our conclusions that we draw from those applications of our baseline calibrated model are going to change. So that's not necessarily saying that any number of these paths are necessarily wrong, but obviously we don't want to have, we want to limit scenarios where we can get to a calibrated model in a number of different ways and we have less confidence in the conclusions that are drawn because there are a wide range of possibilities as to what those conclusions could be. So moving on to the second bullet point there, as I mentioned, past research has provided typical default parameter values that a lot of us folks in consulting rely on when we're calibrating models, at least as a starting point. But the issue with those, particularly relative to modeling freeway work zones, is that they were conducted in legacy versions of Vissim, meaning versions prior to the latest that are available. And within those versions, we don't have these new features that Dr. Turochy mentioned, like being able to model the time headway as a distribution or model the lane change distance as a distribution, both of which we know, at least anecdotally, to be true in the field. So the more gaps that we can fill in with field data driven recommendations for these parameter values, I don't want to say the simpler the calibration process is going to get, because those of you who are modelers on the presentation with us know that you can spend weeks calibrating a micro simulation model, and it's by no means a simple process, but anywhere that we can fill in more confidence in the parameter values that we are selecting towards calibrating that model, the better off that we're going to be in drawing meaningful conclusions. So finally, the overall objective of this two-phased approach that we took on the traffic simulation side of the house was to provide field data-driven recommendations for both modelers and agencies. So for modelers to demonstrate a practical application of this enhanced simulation model, we're calling it, that we've developed from the field data collected from the AI-based system to simulation models, and then taking the application of those models and developing recommendations for agencies that can be applied as they schedule and lay out their work zones in the field. All right, so I'm going to briefly touch on kind of the framework for our analysis and how we went about developing the base Vissim model. As Dr. Turochy mentioned, we're just really going to be hitting the highlights here, and once the final report is published, feel free to indulge in some light reading if you would like to learn more about this. But you know, while the data collected from the AI-based extraction system afforded us with the opportunity to explore modifications to input parameters in our model that we previously couldn't do because we didn't have this data, we didn't necessarily have you know, every piece of data that we'd like to have to develop a flawless model from start to finish where we have a lot of confidence in every model input. You know, in practice, we'll typically go out and collect traffic counts within our study area to motivate our existing conditions volumes. And then we'll take the time to develop a traffic forecast and explore scenarios from there. In this case, we kind of had to piecemeal our input data from a couple of different sources. However, in some ways that adds sort of to the robustness of the study, and it kind of accomplishes one of our goals, which is to develop recommendations that are really generalizable so that somebody who isn't necessarily focused on just modeling a freeway work zone in Savannah, Georgia, can pick up the parameters that we used and the recommendations from our study and apply that to wherever they may be and whatever it is that they may be studying. So the data sources that we primarily used to develop model inputs and get this model off the ground and running, number one is publicly available traffic data from GDOT's continuous count station database. So looking at their database, there were a couple of continuous count stations nearby to the study work zone sites. And while we didn't even have enough field data necessarily to build a full-blown calibration effort where we're trying to calibrate to flow rate and speed and potentially travel time and a number of other measures of effectiveness, we chose these continuous count stations intentionally to be near the study work zone sites so that at least the input demand flow rates that we were using were within the range of that which might have been observed at the study sites when we were collecting the other data that we're using, which is the lane change distance observations and the time headway observations. So down there at the bottom of our little recycling icon there, or our cycle icon, from the AI process video data, we took, as Dr. Turochy mentioned, the time headway distribution and lane change distance distribution data that was extracted from the video at the individual vehicle level, and we used that to inform those same distributions as inputs in our Vissim model. Of course, as I mentioned, given that we don't have every piece of data that we would like to have to form a full-fledged calibration effort, we erred on the side of keeping things coarse and generalizable for the purposes of making these recommendations transferable. So we took the data from the AI-based system and used that as a starting point for our driving behavior inputs, with the understanding that we were going to have to modify those slightly before we felt comfortable that our model was reasonably calibrated to the study sites that we studied here. And the third piece was literature review. So you can see a couple of documents stacked up there, and I promise there were many more, but we thoroughly scoured the literature just to see what the typical default parameter values were for those parameters which we did not have field data for. And we leaned on that to develop those inputs. So the key thing to note about the diagram that's on the right is that we set the geometry of the work zone in Vissim up to model a 6-mile corridor. And that's important because what we kind of saw was going to be needed from the beginning is really understanding the propagation and dissipation of queuing in our network. If we look at, if we go back to the objectives of what we're doing here, and we look at providing recommendations for modelers and agencies, well, the question to ask is, what do each of these parties care about? And also, what do the road users care about? And of course, queuing is at the forefront of an agency's mind as far as impacts at a work zone. And of course, as a driver, that is what is going to frustrate you the most, is sitting in a queue for an extra 15 or 30 minutes, particularly when you're on the freeway where we don't have traffic control and we have limited access, and you're expecting to be able to scoot through at 70 miles an hour. So that's why we set up the model network to be so extensive. And charging right along. So as part of phase 1, which was the sensitivity analysis that Dr. Turochy mentioned earlier, our experiment design included a total of 45 unique cases. So as I mentioned, we had raw lane change distance data and raw time headway distribution data from the AI-based system, and that's what the CC1 parameter is for any of you who don't work in Vissim day in and day out. Knowing that we weren't just going to be able to plug and chug those direct values and get our model to perform the way that we'd like, to where we can say, yes, this is calibrated and we're confident in the conclusions that we're drawing from it. We established a set of ranges primarily based on the literature. So in the case of time headway, a range between 1 second and 1.8 seconds is typical for a 3-to-2 freeway lane closure like we modeled here. Skipping down to the bottom, the lane change distance, the motivation behind, or just to explain what we're showing here with the plus 300 feet, plus 500 feet, plus 700 feet. The tricky thing with the lane change distance is that we have field data to support observations of where the lane changes actually occurred, but the lane change distance in Vissim is an input that determines where a driver will begin to look for opportunities to merge. So the actual execution of the lane change doesn't occur until several seconds after the point at which the driver decides, hey, I'm looking to change. I can see that there's a lane closure ahead. So based on some past literature, what we found is that the average duration of a lane change on the freeway is between 3 and 7 seconds. And so if you do the math, if you're traveling at 70 miles an hour, it's roughly 100 feet per second. So what we wanted to do was take the raw lane change distances, observed in the data, and add plus 3 seconds, plus 5 seconds, and plus 7 to the distances that form each bin of the distribution, so that if driver X wants to initiate their lane change, if driver X is to complete their lane change 1,000 feet upstream of the lane closure taper, they're going to need to initiate the desire to change lanes about 1,500 feet upstream of that location, based on what we saw in the literature. So that's what that is there. And then the safety distance reduction factor, we also varied that between 50% and 100% of the default value, just because that is a parameter that's particularly impactful for influencing lane changing behavior in Vissim. So we felt that needed to be included and that we needed to see how the outputs changed when varying that. So looking at what our objectives were of the calibration component of phase one. So number one, it was to establish a qualitative match to field observed traffic conditions. So we had data from the AI processed video data that said, here's what the flow rate and speed was throughout the day on the day's worth of detailed data we used to inform our inputs. However, that data was only covered a 2-hour window. And I believe we also didn't have the full picture of the onset of congestion nor the dissipation of congestion, which we need to have both of those in order, to be able to calibrate to that. So as you can kind of see in the little thumbnail image to the right, we've got a speed heat map picture there, and you'll see a few more of those over the next couple of minutes. But when I say qualitative match to field observed traffic conditions, that's really what we were looking for, is to see the overall pattern of congestion be similar to that which we observed in the field data, and that we would expect to be typical at the input demand flow rates at this location. And then secondly, we did a more quantitative match to the field observed lane change distance distributions. So that was really the focus of this study. So we focused most of our attention in terms of establishing calibration on making sure that we're matching our outputs in Vissim, or output lane change distances, as closely as possible to the observed lane change distance distributions in our data. And just to briefly touch on that for a second longer, a critical component of that was making sure that we were actually observing, number one, mandatory lane changes. So lane changes occurring in the model because of the presence of the lane closure. So not a discretionary lane change where somebody was trying to get around a vehicle traveling slower than them in front of them. And then number two, that we understood whether or not this lane change was occurring prior to or after the onset of congestion or breakdown in our model. Because, as breakdown occurs and queues build upstream of a lane closure, there is less opportunity for lane changes to occur at the point at which they're desired to occur. So the only thing that we can feed Vissim is the location at which a driver wishes to change a lane. Where that lane change is actually executed becomes more and more influenced by the surrounding traffic conditions after the onset of congestion. So to skip through a couple of the results slides here. So the first piece of the sensitivity analysis, as I mentioned, with establishing calibration, was to determine which of the 45 analysis scenarios that we explored best qualitatively matched the field data. So what you're looking at here is a speed heat map representing the transition area within the work zone. So within the taper area of the work zone, because that's where we had the camera mounted in the field. And I don't have it up here on the screen alongside this to compare to, but what we observed in our video data is that we had congestion occurring midday and persisting for an hour or so and then dissipating. So on the far left, which as you progress from left to right on the screen, on the far left, you have scenarios with a smaller value of time headway. On the far right, you have scenarios with a larger value of time headway. And then as you progress within each of the three scenarios that have the same letter at the beginning, that's where we're adding plus 300 feet, plus 500 feet, plus 700 to our lane change distances. And you can see as you progress rightward across the screen and we increase the value of CC1, we see a lot more congestion in our model. And what we found is, where I've drawn the black box there, that the scenario with a time headway value of 1.2 seconds and that middle modification to the lane change distance of plus 500 feet produced the best qualitative match to field data. So we moved forward with that from there. And the part that was most interesting with phase one is this comparison between, on the right, how we've typically done things in the past, prior to Vissim having the capability of modeling the lane change distance as a distribution, versus on the left, where we're modeling the lane change distance as a distribution. In each case, all of their parameters are held equal. On the left, we've got our field motivated lane change distance distribution. On the right, we have a typical default static lane change distance, which, based on our review of the literature, we found 3,000 feet to be appropriate at a 3-to-2 freeway lane closure. And what you can see is that on the left, we've got our congestion pattern as I described that we saw in the field data, and on the right, that congestion completely disappears. Looking at things a little bit more quantitatively, measuring the maximum corridor travel time observed throughout the simulation, we saw a maximum corridor travel time over the 6-mile simulated corridor of close to 10 minutes on the left, and we never exceeded 6 minutes on the right. So we had an increase in travel time of about 4 minutes between the two scenarios, and from a speed standpoint, we're barely a blip on the radar on the right. And one piece of this that was particularly interesting to me is that if you take a weighted average of the lane change distances that form the distribution used on the left, and you wanted to come up with a static value that represents that distribution, that value would be close to 4,000 feet. I think it comes out to 3,800 feet. So that distance is actually greater than the 3,000 used on the right, yet we're still seeing substantially more congestion in our model. And why that's significant is that typically as we increase the lane change distance, you know, we smooth, quote unquote, lane changing behavior, and we're less likely to see congestion in the model solely as a result of late lane changes. So the fact that, you know, what this says is that even just a few late lane changes, so if the predominant weighted average comes out to be that most of your lane changes are occurring beyond 3,000 feet upstream, but you have a few folks that are waiting until they get to the transition area to merge, that really has a substantial impact on operations at the work zone. So finally, what we were able to do after moving forward with the calibrated parameter set was demonstrate what this looks like as we start to modify some of the other characteristics of our work zone in Vissim. So we looked at a total of 36 cases, and as you can see noted there in the bullet points, what we wanted to do, and as I mentioned before, is create results and draw conclusions that are generalizable and transferable to other situations. So based on the full set of data that we had and that we were working with in developing these models, we ultimately determined that we could look at 3 different scenarios from a traffic volume and truck percentage standpoint. So looking at an urban or a suburban freeway with 5% trucks, which based on our GDOT data mapped to a typical weekend day. Looking at 15% trucks on an urban freeway, which mapped to a typical weekday in our GDOT continuous count station data. And then finally looking at 30% trucks, which represents a rural freeway where we've got a lot of regional truck traffic, as well as regional passenger car traffic, where our overall traffic volumes are a little bit more depressed, but we have such a high percentage of trucks in the traffic stream that we can still see congestion when we close lanes. We also looked at the differences in upstream geometry and lane closure side that James, Cibi, and Lucas summarized earlier as part of the data collected from the AI-based system. And lastly, we varied our volumes in these low, medium, and high buckets that we've dubbed them here. And why this is critical is, you know, if you look at the recommendations that we can make to agencies from a work zone scheduling standpoint, so figuring out where is that threshold at which, if we're expecting demand volumes to approach or exceed this value, where's that threshold at which we should be concerned about closing a lane here, and if it's unavoidable, we should expect delays and understand what those impacts are going to be. Those decisions are both most difficult and most impactful when our demand to capacity ratio is just below or just above 1. So what we wanted to do with our input volume distributions was kind of mirror that case, look at traffic volumes that were just a little bit below the theoretical capacity that we were expecting, as well as just a little bit above. And between 0.92 and 1.08 is commensurate with past literature that we've seen as far as the types of conditions observed in the field in field studies of lane closures. So to get to the highlights, we've got a couple more of these maps in our report, and we've got a ton more data to read through, as I mentioned, if you want to indulge in some light reading at some point once the report is published. But I'm going to look at just 2 quick cases here that kind of summarize the main findings of this phase 2. So number 1, what we're looking at on the screen here is a case with 30% trucks in the traffic stream, and we're comparing a left side closure with a right side closure under straight geometry. And I think really the speed heat map on the right tells the story. So looking at that and looking at the fact that we've got yellows and oranges extending to 4 miles on the top and only extending to 1.5 miles or 2 miles on the bottom, you can conclude that, well, we're observing a much greater impact to traffic operations under a right side lane closure than a left side. And what this really demonstrates is that when we have a high percentage of trucks in the traffic stream and we're closing the right lane in which most of them are traveling, this has a much greater impact on traffic operations on the freeway once that lane is closed. And looking at things quantitatively at these high truck percentages, the maximum corridor travel time associated with the top half there, which has more orange and yellow, was more than 8 minutes more per vehicle on average, which is plus 50% relative to the maximum corridor travel time under a left side lane closure. And the thing to keep in mind with this and the results that we're going to see on the next slide is that the capacity drop after breakdown, and not only that, but also the pre-breakdown capacity and queue discharge rates that are measured in each case differ by no more than 4% between each scenario, yet we see a change in operations as substantial as plus 8 minutes per vehicle on the top relative to the bottom there. So looking at a similar case and comparing curved versus straight upstream geometry, in this case, we're focused on when we have a low percentage of trucks in the traffic stream, as this is where the results were most notable. Under a curved upstream section, the maximum corridor travel time was more than 5 minutes more per vehicle and about 2 minutes more per vehicle under the curved upstream section than the straight upstream section, both when looking at a left side lane closure and a right side lane closure. And I think, as was alluded to previously, these late lane changes that we've referred to a couple of times are more likely to occur when the driver can't visualize the lane closure, which occurs under the curved upstream section. The interesting thing to note here was that we had mixed results at high percentages of trucks in the traffic stream, meaning that in some cases we saw the same trend that we're seeing here on the screen. In other cases, it was reversed. And what we think was happening here is a limitation in our field data for the lane change distances. So we had very few trucks that were observed in the left lane, particularly under the curved upstream geometry case, because that sample size was so small, as well as limitations within Vissim. We think that the impact of just those couple of trucks that get stuck in the left lane when they weren't observed there in the field was kind of swaying the results in some cases and leading to this mixed outcome. So just to sum up here so we can leave a few minutes for questions, the results of phase 1 that we went through that demonstrated the utility of this data that we've extracted from the AI-based system. And what I was most interested in seeing, what really jumped out at me as we were working through this, was just the disparity in model outputs under this calibrated lane change distance distribution versus that under what we typically might apply based on default values in the literature. And what this demonstrates to me is, this parallels back to what I started with. So looking at that maze of potential paths you can take when you're moving from base model to calibrated model. The issue would lie where somebody who doesn't have access to this lane change distance distribution data wants to achieve the same, wants to replicate the same field data that we did, but because they didn't have the data and because they saw no congestion into their lane change distance that they chose, they might start to pull some of those other knobs, like the time headway or the safety distance reduction factor or others that we typically turn while we're calibrating a model. And yes, they may get to the same outcome at the end of the day, but the ultimate conclusions that they draw when applying the model, as we did in phase 2, might differ. So to me, that was really eye-opening and definitely underscores the need to continue to utilize this field data when we have it available, and try to narrow our focus on the ways in which we can calibrate these models. And then finally, in phase 2, we really underscored the sensitivity of freeway work zone traffic operations, and specifically just the fragility of traffic flow. As we saw on the screen, we were only looking at input volumes that ranged between 8% below theoretical capacity and 8% above. Yet we saw such a vast difference in operations that really matter to road users and matter to transportation agencies, specifically seeing those queuing impacts extend miles further, even without actually realizing much of a difference in throughput at the work zone. And what that really demonstrates is the importance of understanding and making sure that we're considering freeway work zone capacity as a stochastic phenomenon, because it truly is. And the difference in measures of effectiveness that we saw really demonstrate that. So finally, to wrap up with some recommendations for modelers and agencies, as we alluded to previously, this, to our knowledge, is one of the first studies of its kind to make use of this lane change distance distribution feature in Vissim. And as a result, there's certainly more study needed. However, the data that we collected as part of the study and the calibrated parameter set that we've used should be applied certainly to 3-to-2 lane closure configurations, but considered for others as well in the absence of better data, just to continue to explore how that impacts the ultimate outcomes of our modeling efforts. And then, as I alluded to previously, truck lane changing behavior, especially that which occurs after the onset of breakdown, should be explored further. If we spent more time on the bar charts that Cibi had up on the screen, what you would see is that it appears that the trucks become more conservative. And when I say conservative, I mean merging further upstream of the lane closure after the onset of congestion, which I think most of us could probably anecdotally agree with, that you see trucks merging over much sooner when they know, not only do they know that the lane is closed, but they can see the congestion building. And so using other features available within Vissim to try and modify the truck lane changing behavior before and after the onset of breakdown could really establish a bit better understanding of the impact this has on the simulation outputs. And finally, for agencies, again, as we've mentioned several times, the key is to understand that significant delays in queues are possible even when demand is near capacity. So we're not well exceeding capacity, and in some cases we may even be below theoretical capacity, but we can still see these massive queuing impacts. And I didn't have it up on the screen, but there was one case that we had where the range between the minimum of the corridor travel time observed during one of the random seed runs and the maximum was 30 minutes. So there was one random seed run where we observed almost no congestion and another where we observed 40 minutes of travel time across the corridor. So secondly, the field data collected as part of this project, and I think Cibi hinted at this as well, suggests that drivers really will wait longer to change lanes until they can visualize a lane closure downstream. I think anecdotally, we've gotten to the point where we've so overused static signs and we don't cover them or remove them when they're no longer applicable that folks just tend to ignore them. And I'm not saying I'm not guilty, but until a driver can visualize the lane being closed in front of them, it's less likely they're going to change lanes. And because of that, for safety and operations, we shouldn't be locating our transition area to begin less than 1/2 mile downstream of a horizontal curve. You know, if possible, we should move that upstream of the curve or make it so that we know that our lane closure isn't beginning until at least 1/2 mile downstream of the horizontal curve. So with that, I'll switch it back over to James here to do some wrap up, and then we'll get to some quick questions. I'm sorry for only leaving a couple minutes here for us.
Okay, thank you, Nick, and thanks, Dr. Turochy, and then Lucas and Cibi. So I think I will not repeat the previous summary. I just want to point out that so far, I think based on this research study, the research outcome is quite promising. And so what we recommend, the recommendation for future research is including, now there's a preliminary, the automated extraction module there. So that is preliminary version. So it will make sense to refine and deploy the proposed AI system for work zone driver behavior and traffic information extraction with a pilot study and using existing traffic camera, as earlier mentioned about on the selected state, and also develop a QA/QC tool to assist transportation agency quality control. So I think kind of gradually rolling to the deployment too. The other one there is to collect additional data on the work zone scenario. Earlier you can see Cibi, we have a different scenario there, but I think some of those there is a limited cases. So we hope that to have a chance to collect additional data to confirm the preliminary lane change distribution finding and a further study, as well as support the simulation like Nick and Dr. Turochy mentioned about. And so those are the recommendations. With that, I would like to open questions. Any people have a question? Yeah.
Yes, we have a couple of questions.
Okay.
I would like to answer them. They're directed. So first question was construction worker fatalities are critical work zone safety. Wondering if there is any updated road construction worker fatalities for Georgia and Alabama for 2019. Yes, the worker fatalities are critical in the work zone, and as of 2019, the worker fatalities at the national level was 134 worker fatalities. And further information state-wise can be found at workzonesafety.org, and that gives individual state-wise distribution. And the second question that we received is in terms of slide 18, where different scenarios were presented for low, medium, and high traffic density. Was there any threshold value for low, medium, and high traffic density? That's a great question. Yes, we did use a threshold for the traffic densities. So we used both the numbers, the volume, and also the speed to classify them. And for the low traffic densities, it was about 30 vehicles per mile was the and below was taken as low traffic density, and the speed at those sections were about 70 miles per hour, and the medium was between 30 and about 150 vehicles per mile, and in our case it was around 60 vehicles per mile, and the speed was about 55 miles per hour. And for the high traffic density, the number was 150 vehicles per mile, and the speed was about 25 miles per hour. So that is the distribution that we used in this case.
Any further questions? If not, I think since this webinar ended now at the exactly 1 o'clock, so I think we are kind of right on time now. So please feel free to enter the survey, and if you have a question, feel free to contact us. And this is the list of the upcoming webinars. So kind of just showed it to you so that if you are interested in attending the upcoming webinar. So with that, anything from the speakers? So if not, then we are going to stop the today's webinar here. Okay, thank you very much. Bye.